You should be able to freely unmute yourself. Please don't take advantage of that. But if you have questions or whatnot, by all means. I don't normally look at the chat, so if you got the chat up and your microphone doesn't work, somebody yell out if somebody has a question in the chat. If you're going to do the Student of the Month thing, then you can just leave yourself unmuted and answer all the questions. Remember, the first day of a new unit's the easiest, right? So tomorrow, if you didn't print anything out, you will get this bonding packet. Now, I know it doesn't have this on this if you just printed out the quick edition. So let's go ahead and review real quick valence electrons. If we're talking about an element, for example, lithium, it has 3 protons and thus 3 electrons. Protons are in the nucleus. Remember, 2 electrons in the first energy level, and then we only have 1 left over, so 1 electron in that energy level. If we have something like fluorine, it has 9 protons and then thus 9 electrons. We have 2 electrons here. 2 from 9 is 7 electrons. And then we talked about something called the octet rule. And we said that they tried to get this for you in 5th, 6th, 7th grade, whenever. But it's basically to get 8. In reality, it's to get 8. Let's make this 7 better. If you're talking about one of the rings past the first one. The first ring only holds 2, so that can get you an octet just as easy as the 8 can. Then we talked about fluorine having a high electronegativity. And we know that lithium has a low ionization energy. So the nucleus of this fluorine will attract that electron, pulling it off, giving the fluorine 8 electrons here, which fulfills the octet, and giving the lithium here 2 electrons, which fulfills the octet for it. A lithium positive 1 cation will pair up with a fluoride negative 1 anion through an electrostatic charge, and we will get lithium fluoride. Now, if these were uneven, for example, if this needed 2, like oxygen, then it would take 2 lithiums, right? And then we'd have Li2O, stuff like that. Remember, this only occurs with metals and nonmetals. That's ionic bonding. Ionic bonding is pretty straightforward. We discussed it a lot when we were sitting there looking at like calcium chloride. We need 1 calcium for every 2 chlorides. What happens? Well, the calcium loses electrons, the chlorides gain electrons. Pretty simple stuff there. We're not going to focus a lot on the ionic bonding because it is just electrostatic force, and we covered it mainly with the naming of stuff. We're going to focus on covalent, or what's also called molecular bonding this time. If we take oxygen, for example, oxygen has 8 on our periodic table. We have 8 protons. There's 2. That leaves us with 6 here. To get this fulfilled to be an octet, the oxygen needs to gain 2 electrons. Now, there is something different. If we look at hydrogen, for example, 1 proton and 1 electron. Both of these have a decent ionization energy. Hydrogen's not going to be willing to lose an electron as easily as these metals are. It can, but it's not going to do it in this case against oxygen. What's going to happen is, and it might be better for us to look at a box diagram for this. For the oxygen, we have 1s2, 2s2, 2p4, right? 1, 2, 3, 4, 1, 2, 3, 4. And for the hydrogen, we have 1s1. Well, what's going to happen is the oxygen and the hydrogen are going to both fulfill their octet by not exchanging electrons or losing or transferring electrons, but by sharing. If we imagine we have the oxygen here, and we have a hydrogen here, and a hydrogen here, imagine that these two boxes and these boxes right here are right here. One of these electrons is from the oxygen in each box. The other electron is from the hydrogen. This is called a shared pair of electrons. That's also called a bond. The oxygen also has, if we take a look, we're not worried about these guys because they are not in the valence shell. It also has two unshared pairs. 1, 2, 3, 4. Now if we count all these up, 1, 2, 3, 4, 5, 6, 7, 8. The oxygen has 8 electrons, which is the octet. We count them up for the hydrogen, 1, 2. Each of these has 2 electrons for the octet because hydrogen doesn't need 8. It fulfills that first energy level. That's a lot. Any questions there? All right, so to start this out, they give you the electron configuration here of P. 1s2, 2s2, 2p6, 3s2, 3p6. If we're trying to find the valence electrons, we look for the highest number and we add these together. 6 plus 2, I'm sorry, not 3p6, 3p3. Sorry about that, I was ahead of my mind. 2 plus 3 is 5, right? And remember, we can use our periodic table to find that as well. Here's P, 5a, 5 valence electrons. You know which one's faster? Looking at the periodic table. Hydrogen is 1s2. I'm sorry, geez. Hydrogen is 1s1. I'm sitting here adding up the octet in my mind, and I apologize for it. If we were to make our box diagrams, we would have the same thing, but again, that takes time. So what you can do is you can sit here and say, okay, we have 3 of these hydrogens. That's a total of 3 valence electrons. And we have 2 plus 3, which is a total of 5 valence electrons for the phosphorus. 5 plus 3 equals 8. So the bonding for this situation is going to have 8 electrons to kind of work with. We talked very briefly about the Lewis structures of P, and we would sit here and put them on 1, 2, 3, 4, 5, 6, 5. And then we would have basically 1, 2, 3, 4, 5. That's all we have. Well, if we were to write this out, here's 3s2. 1, 2, 3. Here is our 3p3. So it needs 3 electrons. Well, we have 3 hydrogens here. So what's going to happen is we're going to have bonding with these hydrogens. Again, we could draw these boxes out and fill them in, but that's not what we're being asked to do here. If we take a look, we have 2 extra electrons on that P, which will give us our total of 8. 2, 4, 6, 8. We would say that the P has 3 bonding pairs, or 3 bonds, and 1 lone pair. Crazy enough. The rest of this basically just has NH3, and all it wants you to do is go ahead and count up the valence electrons, which is easy. Nitrogen is in group 5a, hydrogen is in group 1, but since there are 3 of them, we end up with 8. Sulfur dioxide. Sulfur is in 6a, oxygen is also in 6a, but there are 2 of them, so we end up with 12 plus 6, which equals 18. Gets more complicated and more complicated as we go on, but all you really need to do right there is just add up the valence electrons. That's the key for this exercise here. The other thing we want to be able to do today is to draw some basic structures. So again, we don't need to write out the electron configuration, but we could do that. Bonds can electrons can be represented as 2 by putting a pair or a line, or as dots, and you can pair up the dots too. It takes a lot longer to draw them as dots as time goes on, so you'll probably end up just drawing lines in the end. If a pair or a line is drawn between, then that is a bond. If a line is not drawn between, then that is a lone pair. And you can draw them either way. Page 4 has some practice problems on it. The first one is HF, hydrogen fluoride. Hydrogen has 1. Fluorine is in group 7A. 1 plus 7 equals 8. There is no real center here, so all we're going to do is we're going to connect them. Out of the 8 electrons we have available, we've already used 2 right here for the bond. Remember, hydrogen is fine. It only needs 2 electrons to fulfill that energy level requirement. Fluorine needs S and P filled, so here we have the 2, 4, 6, 8. That would be the Lewis structure for hydrogen fluoride. The next one they have, it gets a little bit more complicated, would be nitrogen triiodide. Remember, we have to use prefixes with this. Now, the number one question is who we put in the middle. Well, if you only have one of something, it goes in the middle. Nitrogen. Nitrogen brings 5. Each of these brings 7, but there are 3 of them. So that is 21 plus 5, which equals 26. One iodine nitrogen bond, 2, and 3. So out of that 26, we've just gotten 2, 4, 6 taken care of. That leaves us 20, 2, 4, 6, 8, 10, 12, 14, 16, 18. The nitrogen does need an octet. It only has 2, 4, 6 right now, so there's that last 20. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Remember, the nitrogen brought 5. 1, 2, 3, 4, 5. Each iodine brought 7. 1, 2, 3, 4, 5, 6, 7. Right? Everything is fulfilling the octet. Count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's the original 26. Right? Let's do one more. This one has CCl4. So if you would, go ahead and try that on your own. Just real quick on your blank piece of paper. Carbon is in group 4A. Chlorine is in group 7A. Carbon is in group 4A. Chlorine is in group 7A. Four plus 4 times 7. That's 28 plus 4 equals 32. We're going to put carbon in the center because it is unique. That's the term we use for something that's all alone. The chlorines will go around it. This is what's called a skeleton structure. It only includes the bonding electrons. So currently carbon has 4 bonds. We have a total of 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Each chlorine has a total of 8, and the carbon also has a total of 8 electrons around it. Remember the carbon's 4? 1, 2, 3, 4. One of each of these bonds is an electron from the carbon. The chlorines each bring 7 to the party. 2, 4, 6 is going to be the ones that are already paired up for the chlorine, and this extra electron right here is going to be that 7. One more, NH3. Try that on your own if you would. Nitrogen is in group 5A, hydrogen is in group 1A. If you needed a little bit of help there. That's going to be a total of 8. Nitrogen in the middle. Why? Because it is unique. Hydrogen's all around. Now here's the tricky thing again. We never want to see anything other than one bond going to a hydrogen. Remember, it has one S1. All it needs is one S2 to fulfill the octet rule. If you're putting lone pairs on hydrogens, then you are wrong, wrong, wrong. The nitrogen has 2, 4, 6 currently. It needs that 8. So we're going to put it right here. And again, if we look at nitrogen, it is 2s2, 2p3, 1, 2, 3. Those are the 3 that the nitrogen bought. That's that 2s2 right there. And then the hydrogen itself brought 1 each time to make these bonds. It has 3 bonds and 1 lone pair. That's going to be important for later. We always just look at the middle guy. That's going to allow us to do our shape. I want to try one more and see if we can't push. O2. That's 6. It's in group 6A. This is an element and a molecule that you have a lot of familiarity with, at least your body does. 2 times 6 equals 12. So there's our 2. 4, 6, 8, 10, 12, 14. This poses a problem. We have too many electrons to give everybody the octet. We have 14 showing. We only have 12 available. This is 2 extra electrons. That's no good. That means that we need to make another bond somewhere, a double bond. And when we make that double bond, in order to get rid of 2 extra electrons, we have to take a lone pair from each of these. 2, 4, 6, 8, 10, 12. A lot of times in your earlier years, they would have told you that oxygen likes 2 bonds. It's true. We have something called the honk rule. Hydrogen and halogens like 1 bond. Oxygen likes 2 bonds. Nitrogen likes 3 bonds. Carbon likes 4 bonds. The reason is whenever you look at their electron box diagrams, hydrogen is only going to have that 1. Oxygen is going to have 6. 2 boxes. Nitrogen is going to have 5. 3 boxes. Carbon, right? It's in group 4A. Strangely enough, you're not going to believe this, but things get a little bit weird. And this is called an sp3 hybridization. We don't have to worry about that yet, but we have 4 empty boxes. 4 bonds for carbon, 3 bonds for nitrogen, and oxygen would have 2 bonds. Hydrogen and halogens would be different because they have that 7, but we'll get there later. This is called the Honk rule. This brings us to being able to see into the future. If nitrogen likes 3 bonds and we have nitrogen in 2, the most prominent gas in our atmosphere, it has 10 electrons, 5 from each. What are we going to need to do between nitrogen and nitrogen? Anybody? It likes 3 bonds.
Put 3 bonds.
You got it, Caroline. Check it out. 2, 4, 6, 8, 10, 12, 14. This time, how many are we over? We're over 4 electrons. Last time I told you if you're over 2 extra electrons, you need another bond. For every 2 electrons over, you need another bond. So this nitrogen is going to have 3 bonds there. Now, last question. We have about 2 minutes, I think, left. Student of the month question. Notice how I put all of these electrons around these guys. Student of the month question. Why did, instead of leaving this like an ET face, why did I put it like this? Anybody? Or why did I write nitrogen like this versus writing nitrogen like this?
It's even on both sides.
Symmetry is important. Who said that? Symmetry is important, but it's not the main rule. What are making up the bonds and what are in these lone pairs? This is the heavy-hitting class, but some of you guys are too shy. Just go ahead and say it. What are making up these bonds? And what are in these lone pairs? What am I?
Electrons.
Electrons. Good. So why did I rewrite it instead of leaving it like this? Why did I rewrite it like this? And why wouldn't I write it like this? I would write it like this.
Is it because, like, when there's a bond, then the boxes get filled up? So then there's, like, less available boxes?
You might be thinking on the right track, but it's not 100% there. That's why this is Student of the Month question, right? It's all part of what we call this theory. What are the charges of the electrons?
Negative.
And if I bring negatives too close to one another, what are they going to do?
They go away from each other.
You got it. They're going to repel. This stands for the valence shell electron pair repulsion theory. They repel, so we want to make sure that they are three-dimensionally repelled as much as they can. For your assignment, if you would, you don't have to do it today, but it needs to be done Friday before. It's just these 4 right here. If you want to get a screenshot real quick, you're going to draw these. And then you're just going to submit that right there. If you want to get a screenshot, you can do it on regular paper or whatever. And I'm going to leave it up there. This class is just the first half of the class. So you guys are more than welcome to head out. If you want, you can stay and ask questions. Totally up to you. This is how the attendance will be determined. So by Friday, please submit this. And it's not Friday midnight. I have to change that. It's Friday by 4 o'clock. Because that's the last time I can change attendance for today. Thank you guys. Hopefully tomorrow we'll be in there.